Hi everyone. So today we are going to discuss about the sizing of propulsion motors used in an electric vehicle. So when coming to this sizing, so here we are going to study some basic motors used in electric vehicle and how to decide their size. Okay. So coming to here, basically electric motors has have some few limitations why the size plays an major role. Whether to have reduced size or whether to have higher size depends upon the following restrictions. Okay, so most of the electric motors used in electric vehicle drivetrain has a maximum speed limit, so they can run only up to 12,000 rpm rotations per minute. So due to this restriction, so whenever if you rotate the rotor of induction motor more than this speed, it undergoes some sort of centrifugal forces. Okay, so they undergo some sort of centrifugal forces which create an imbalance in the rotor. Okay, and the rotor may mechanically fail. So the rotor is rotating with higher speed may undergo centrifugal forces which makes the rotor to move away from the wheel, and the rotor of the motor may mechanically fail. So to reduce this failure or to reduce this mechanical failure, so you should not run the you should not run the motor of an electric vehicle more than 12,000 rpm. So one more restriction is, so we have some hall sensors. So if we take an BLDC motor, so this is what I'm saying. So the size of the motor depends upon the maximum speed you operate. So if you want to, we cannot drive this motor more than the speed, we have to drive less than the speed. So we have the restriction on the speed. So this is how an PMSM motor and BLDC motors are there. In this is the case what I discussed in, we have to reduce this mechanical failure. That's why we should run the motor only in the speed range of 12,000 rpm. The next limitation of BLDC motors is, here you have the permanent magnets on the stator and you have the electromagnets on the rotor, and Hall sensors are there at the rotor part. Okay, so we have the Hall sensors which are located on the rotor part. So when you are trying to rotate with higher speed, so they cannot sense the speed of the stator. Okay, so the Hall sensors is unable to sense the speed of the permanent magnets automatically due to this effect presence of Hall sensors. So within the available sensitivity, so they cannot also, we cannot run these motors, especially these BLDC motors or permanent magnet synchronous motor beyond this RPM. This is the one of the two problems which are restricting to have a bigger size of propulsion motors. So we have to design the motors only the speed range of 12,000 rpm. And next we have is the performance of an electric motor. How to decide the performance of an electric motor is measured by the, so already if you want to know about this BLDC, so in my channel you have an link. So how to run a permanent magnet synchronous motor and how the power is generated, I will leave you in the card. You can see there and bulb will glow. So it's nothing but by using an synchronous motor, I have been using this synchronous motor as an generator, and I have been running regenerative braking. I will leave in the card, you can see there. So now coming to this motor category, so what is the problem with this motor, why they are unable to run? Okay, so the performance of an electric motor, so I have to decide the performance of an electric motor. So it is restricted by, or it is measured by three quantities. One is the torque and power handling capability. So it is decided by the torque and power handling capability. Next, the performance indices. To determine the performance of a motor is, the constant power speed ratio. Okay, so constant power speed ratio is very simple to understand. So constant power by speed ratio. So this I can write down power divided by 2 pi n divided by 60. What is this? Power by omega is nothing but torque. Or I can say that power is equal to torque into angular velocity. So here that's what is called constant power by speed ratio is nothing but indirectly it has to operate with constant torque. So you already have the dynamics of an electric motor, how it operates in constant torque region and constant power region. Okay. So this is how it has to operate. So now, and next one is the performance indices of electric motor is directly proportional to the size of the electric motor. So based upon these three performance indices, we are going to decide the performance of an electric motor. So first, let's try to discuss about the constant power torque handling capability. Okay. So the first one is constant power and torque handling capabilities, whether it is able to handle it or not. So let us try to see here. So in order to understand, I'm trying to draw the speed, power, torque characteristics. So I'm taking the three quadrants. Here I'm going to have the speed on the x-axis. Here I'm going to have torque, and here I'm going to have the power. So we have the relation for torque is equal to power into angular velocity. So in this case, so here I'm going to consider a critical speed of 1500 rpm. So up to this point, so here I'm going to assume that, so here I'm going to assume the torque is constant. Whenever the torque is constant, we have a relationship. So torque is equal to power into angular velocity. It can be written as 2 pi n by 60. So here torque is constant, and I can write down, sorry, so this is like a small modification. Power is equal to torque into angular velocity. In this case, whenever power is equal to torque into angular velocity, we are considering torque is constant. Therefore power is directly proportional to 2 pi n by 60, and I can say that power is directly proportional to speed. So here I'm considering this region as a constant torque region. So up to this speed, you can see here the curves what you're going to have, power is proportional to speed. So after this point, I'm going to assume that, so power is equal to torque into angular velocity 2 pi n by 60. So here the relation I'm going to take the power as constant. So this is nothing but power is constant. So constant divided by 2 pi n divided by 60 is equal to torque. So now torque and speed are inversely related. So now we are going to get the characteristics. So here I assumed the torque is constant and power is rising linearly, and later power is constant and torque is inversely proportional to 1 by n. Okay, so these two relations are very important. So this is what happened less than the rated speed, this is what happened after than rated speed. These are called power, speed, torque handling capabilities. Same, now we are going to have an graph of these characteristics. How I explained here, when you try to draw the graph, so this is nothing but speed, this is nothing but torque, and this is nothing but power. So I'm going to have an peak torque, this is called as peak torque, constant torque, and then you're going to have the next torque, which is nothing but called as intermediate torque or irregular torque. So this is called irregular or intermediate. So intermittent overload operation here. And next one we are going to have a different torque. So this is having this kind of operation. So now when you see here the normal operation at different torque, so I'm drawing this. Let us take under normal condition of constant torque of 150 Newton meter. So this is under 225 Newton meter constant torque, and this is under a peak torque of 375 Newton meter. So here I am going to call this as peak torque, and this torque I am going to call it as irregular torque. So this torque is called irregular torque. So now we want to establish the relationship between all these torques. So we are going to have the three curves. So first curve, which is nothing but a continuous rating. So continuous rating, where they generally we call it as the in electric vehicle as a normal mode of operation or economic mode of operation. So this we call it as an economic mode of operation. So here the electric motor, so this I'm going to take it as this operating with a constant speed of 120 Newton meter. Here the electric motor can be operated in an continuous rated region. So this is nothing but a continuous rated region. Second one is intermittent overload operation. So we are going to suddenly load, which is called intermittent overload operation. So intermediate means this suddenly we are changing the mode of operation of electric vehicle from normal modes to sports mode. So when you change the speed, the vehicle may be driven with around 120 kilometers per hour. So at this speed, it may be driven. So this generally happens when you want to change the speed. This will also happen in a lesser time. And here, the electric motor will be operated in this region for a very short duration. So this operates only for an short duration. The time taken to transfer from normal mode to sports mode is also of small duration only it can transfer. And what is this magnitude of intermediate is this intermediate overload operation is 1.5 times of continuous rated output. Now let's try to see here. So this is called continuous rated output. So this is 150 times. So 1.5 means 150 times of continuous rated output is 150 Newton meter. So this is approximately 225 Newton meter. So in this mode of operation, the electric vehicle will be operated for shorter duration, and this is generally and not doesn't happen continuously. It happens in irregular, and here we have overloading operation. So then it operates in intermediate overload mode of operation. So third mode is, so now I want to drive the electric vehicle in higher speed. Then I want to operate it in peak overload operation. So I need to operate it in peak overload operation, and this we can claim as I need to operate the electric vehicle in hyper mode of operation. Hyper mode of operation means, so here I'm running in this economic mode with 60 kilometers per hour. So here I'm driving with 120 kilometers per hour, but I want to operate here with 180 kilometers per hour, so which is very dangerous. So in this peak operating mode, so here also the electric motor can be operated in this region for a very short duration. So it can operate only in very short duration, and it will be in the range of some 3 minutes. Okay, we may shift, but the time taken to shift is very less. In this peak operating condition, I can specify the time of operation is very less, and here we have the peak output of the motor is, it is 2.5 times of continuous rated output. So this is 2.5 times of 150 Newton meter. So this is 2.5 times means it is 250 times of 150 Newton meter, which will resembles 375 Newton meter. So here you can see here motor has to operate in continuous mode, and it has to operate in intermediate mode, and it has to operate in peak mode. And when you reach the highest speed, then you can move from hyper mode to sports mode, and sports mode to normal mode. So you can switch on this operation. Okay, so this is how we need to operate the electric motor in different modes of operation. So this is called as how the electric motor operates in different modes of operation. So hope so this not that much simple to understand, because you need to understand the speed power torque characteristics. This is called the speed power torque characteristics of an electric vehicle. So this region, this is called the speed power torque characteristics of an electric motor. So initially what happens is, under lower speed only, the electric vehicle can offer higher torque. As soon as the speed is increasing, the torque offered is less. As soon as you're running with maximum speed, the torque which is offered by the electric vehicle is very minimum. When you're running with the highest speed, the torque offered is very very minimum. That's why we call this as the speed power torque characteristics of an electric motor, and these characteristics are similar to that of an internal combustion engine. That's why this is very popular. So if you understand the dynamics of this electric motor, it's very simple to understand. So here you had understood the this is the motor. How to decide the size of the motor is based upon its maximum speed. So I want to drive the electric motor in a maximum speed range of 12,000 rpm. It has a problems of it cannot be driven for longer higher speed of 12,000 rpm due to its centrifugal force, and due to presence of Hall sensor, we are restricting the maximum speed of a motor to 12,000 rpm. So this is an example of an permanent magnet synchronous motor, and this is the presence of Hall sensor on the rotor of an BLDC motor. So this Hall sensor cannot detect the speed of the stator. Due to this, we cannot run with higher speed. Now coming to how to evaluate the performance of an electric motor is based upon its torque, speed, power handling capabilities. So how to understand this constant speed, power, torque capabilities is like this. Okay, so these are constant speed and power torque capabilities. So we are going to understand what are the different modes of operation in an electric vehicle. One is continuous rated, next one is intermittent rated, next one is a peak overload operation. That's how the motor has to switch its one mode of operation to another mode of operation. Now let us try to discuss about next one is a constant speed ratio. Okay, so next, performance indices of an electric motor to be used in an electric drive is constant power speed ratio. This is very very important. Already I discussed. So we have the relation power is equal to torque into angular velocity, which is 2 pi n by 60. So constant power divided by 2 pi n divided by 60 is nothing but constant torque. Okay, so here we need to operate it in this constant torque region. So how to operate? Let us try to experience. So here we have the four quadrant operation. If you want to understand this four quadrant operation, in our lecture videos, you can see how an chopper operates in four quadrant and what is the importance of a four quadrant operation in electric vehicle drive. You can see in our I will leave in the card. You can check from our lecture video playlist. So what is this constant power by speed ratio? Is nothing but torque ratio. How to understand this torque? So in order to understand it, let's try to understand the four quadrant operation of an electric vehicle. So here we are going to have the four quadrants, and x-axis I'm going to take the current. Here I'm going to have the negative current, and here I'm going to have positive voltage. Here I'm going to have negative voltage. So here I have the formula. Torque is directly proportional to flux into armature current. So I can write down current and torque are available here. Here negative current and negative torque. So here voltage is directly proportional to speed. So I can write down voltage and speed are positive. Here negative voltage and negative speed. So these are the quadrants what actually we have in this mode of operation. Let's try to understand our electric vehicle is trying to operate in an first quadrant. So where this is called as a forward motoring mode of operation. In this forward motoring mode of operation, we are going to understand that our electric vehicle is propelling in forward direction, and the x and y quadrants here current is positive as well as voltage is positive. I can say that torque and speed are positive. So I'm saying that the electric vehicle will be operated in forward motoring mode in first quadrant. And here now we need to move from first quadrant to second quadrant. In the second quadrant, the electric vehicle motor which was running, I mean our electric vehicle is running with an clockwise direction, and it is running with a speed of take a speed of 100 kilometers per hour. Okay, so here it is running with 100 kilometers per hour, and we remove the complete acceleration. So from this point to this point, it has to come to a speed of 0 kilometers per hour. So in this it was acting like an motor. Okay, so now it need to, so in this case it was acting like a motor, and now this motor will try to act like an generator. So why? Because it's already running with 100 rpm. Slowly from 100 it comes to 90, 80, 60, 70, 50, 40 and 0. So this period we are going to call it as a regenerative mode of operation, and which was acting like a motor will now try to act like a generator. So this is called the second quadrant of operation. Here you are going to have x and y coordinates. Here you are going to have a current of minus current and a speed of positive speed. If the current is, I mean, we are going to have, let's try to write down currents and voltage. Current is minus I and voltage is positive. So minus current, I can write down it as a negative torque and positive speed. Negative torque is there, automatically this is nothing but a generating mode of operation. So here we are going to call this as a, the motor will try to continue in forward direction. That's what is called forward regenerative braking mode of operation. And from this mode, once again it comes to the next mode. So here in this third mode, the electric vehicle will try to move in reverse motoring mode. So the direction is reversed. I can say what are the x and y coordinates. Here the current is minus I and the voltage is minus v. This minus I can write down it as minus torque, and speed I can write down it as minus n. In this, it is trying to rotate in counter clockwise direction. So this is useful like an parking. So if you want to park an electric vehicle, if you want to make the motor to rotate in opposite direction, for example we are moving in this direction, okay, so but you want to come back, I want to operate this in reverse motoring mode. This reverse motoring mode helps us in parking, which offers a negative current and negative voltage across the motor terminal, offering an negative torque and negative speed. Now it is running in reverse, it's going back. So in this reverse, when it's going back also, it try to, the vehicle will try to continue in reverse mode only. And here in this reverse mode also we can operate in generative mode. Therefore we are going to call it as reverse regenerative mode of operation. Here the currents and voltages are nothing but current is positive, here voltage is negative, and this current we are going to call as positive torque as well as negative speed. So you can here see here torque is positive but the speed is negative. That's why in this reverse regenerative mode also it can generate the power. So this is what the type of operation is generally taken care by the chopper, which is called class C chopper. So when you are trying to run the vehicle, it will be first quadrant. So as soon as you apply the brake or if you remove the acceleration, it comes to second quadrant. So when you are increase the acceleration, once again it comes to first quadrant. So when you are in this motoring mode, when you are driving, if you want to move the vehicle backward direction, then it comes to third mode. Actually this mode is not there in electric vehicle, only these three modes are there. Okay, so this is called as a constant power, and speed is nothing but constant torque. So this is called the constant power and speed ratio of an electric motor in different modes of operation. So coming to the next performance indices, we are discussing this performance indices. First one is power, torque and power capabilities. Next one is constant speed power ratio. And next one is electric motor sizing. So third performance indices is electric motor sizing. The size of an electric motor is directly proportional to the torque developed. So this torque can be written as a constant of proportionality as K and an A as ampere turns, and one more as the flux density as flux per unit area multiplied with diameter of the rotor multiplied with the length of the electric motor. Okay. So here is K is called as constant of proportionality, and Ni is called as ampere turns, and this is called as flux density, flux per unit area, and D is called as the diameter of the rotor, where L is called as the length of the electric motor. So the length of electric motor. So based upon all these factors, the number of turns, the current carried by the armature winding, the flux and the diameter, the torque is going to decide. Based upon this torque development, we are going to decide the size of the motor. So in the case of an this is like a universal formula. In the case of a DC motor, the torque given is 0.159 flux into, I mean, flux in the field winding, armature current in armature winding multiplied with number of conductors multiplied with P by A is nothing but the units you are going to get in Newton torque. So based upon the torque requirement, you are going to decide the size of an electric motor. So the torque requirement is nothing but torque by, the torque requirement is nothing but the power by speed ratio. So all these performance indices plays a major role in deciding the size of an electric vehicle. That is called the sizing of an electric motor. All these performance indices will help us in deciding the size of an electric motor. So if you feel the content is really useful for your academic, please give a like and please share the contents with your friends. And if you have any doubts, let me know in comment section. I can answer your doubts. And if you're watching the channel for the first time, this is a channel for the help of students and faculty. Please subscribe the channel. Yours obediently Ram. We'll meet in the next video. Thank you for watching.